This is the second invited speaker that we have in this online seminar series about machine learning needs mathematical optimization. We are very happy that there are loads of people joining as of now. Yeah. So I will slowly introduce our speaker today. So it's Bart Baesens from the Katholieke Universiteit Leuven. Actually, Bart and I know each other for a long time, lots of things to say about him. The first thing is that he has worked intensively on big data and analytics. He has worked in very important applications such as credit risk marketing, and today he's going to talk about fraud. I'm sure that you have encountered some of his papers because he has more than 250 co-author papers. He has written quite a few books. I myself teach in the MBA program, also analytics and big data, and I use one of his books. So it's one of the, I believe, 10 that he has. And they have been translated to many languages, just such as Japanese, Korean, Russian, etc. I would like to mention that, as you know, one of our interests in this European project NeEDS is interpretability. So he has a paper, a classic paper in management science, written in the early 2000s, and that is basically a breakthrough in the field of interpretability. But he has also written very recently other papers in management science, and I'm sure that we will see those in the long list of references. Bart has also received prizes from different OR Society, including our European OR Society Euro. So I think we all know that we are in front of a great speaker, and I would like to give you the floor, the E-floor, Bart. And thank you very much for accepting the invitation to talk today.
Thank you very much for this kind introduction, Dolores. As Dolores said, my name is Bart Baesens. I'm connected to the Catholic University of Leuven, which is a university in Belgium. It's obviously one of the best universities in Belgium. I'm actually not aware if there are any others, but anyway. This talk is situated within the NeEDS project, which is a network of European data scientists. And I would like to especially thank Dolores and Emiliano once again for hosting me and for doing this project with our university, because it has created some really nice, interesting research opportunities and collaborations. I will start with the boring part of my presentation, hopefully the boring part, which is the introduction about myself. So I'm a professor of big data and analytics here at KU Leuven. I'm also a part-time lecturer at the University of Southampton in the UK. My research is big data and analytics, and I study this both from a theoretical perspective. That means that I study the development of new algorithms, new techniques, new ways of analyzing data, but also innovative ways of applying that data. And I typically do that as any supervisor with a collection of PhD researchers, some of whom I noted are also attending this talk. So I study applications in credit risk. That was my primary field of expertise, but I also work in fraud analytics, in marketing analytics, and in network analytics. If you want to follow me, feel free to connect on YouTube, Facebook, or Twitter. I have a research community which is called dataminingapps.com. I also recently started my own online teaching platform, which I will tell you about in a minute. At the bottom, you see some of the books that I've written. If you want more information about the topic, or if any of those books, feel free to let me know. Here's the online course platform that I recently started. I'm actually a part-time professor at the Catholic University of Leuven. Next to that, I consider myself somewhat as a mini entrepreneur. I started this platform, this online learning platform, offering all kinds of online courses like machine learning, like text analytics, Also a course on fraud analytics, and actually much of the material that I cover in today's talk is also covered in that fraud analytics online Blue Courses course if you would be interested. So let's immediately cut to the chase with the overview. So first I'm gonna define fraud because it's a multifaceted problem that you can study from different angles, which are very important to be aware of if you want to tackle fraud with analytics. Then briefly summarize the key approaches to tackle fraud in an analytical way. And then I'm going to zoom into a few pieces of research that I recently conducted with some colleague researchers. The first being cost-sensitive logistic regression. And then we're going to go into data engineering and more specifically feature engineering, and we're going to talk about time features and social network features. Note that these are just two very limited topics related to fraud analytics. There's much more to say about it, more specifically about how to boost the performance of your analytical fraud models, but I chose these two topics because I consider them to be really very important. How can you define fraud? Well, this was a definition that was put forward by one of my ex-PhD students, Veronique van Vlasselaar, and myself already in 2013, where we defined fraud as an uncommon, well-considered means intentionally, imperceptibly concealed. Obviously, you want, as a fraudster, you want to be as much as possible hidden, be hidden within a population of regular customers or a population of regular transactions. It's time evolving because fraudsters always try to beat the fraud detection mechanism, and it is often carefully organized, which means that oftentimes fraud will occur in a collusion setup between different parties, which opens up very interesting perspectives for social network or network analysis as such. It appears in many types and forms. Insurance fraud is one of them. We've studied insurance fraud, and I'm going to report on a case study of insurance fraud as we progress through the presentation. Credit card fraud is also something that we extensively studied. There's counterfeit, there's corruption, there's credit application fraud, etc. So there's various types of fraud. And the way to tackle that analytically is either using an expert-based approach. An expert-based approach is usually based on the expert's intuition, business intuition that he or she has acquired throughout having many years in the field of insurance fraud, in the field of credit card fraud. An expert-based approach is usually articulated as a set of if-then business rules, right, which have been manually tuned, not based on data, but based on expert intuition. Not a bad word about this approach, because some of these expert-based approaches still work very well in certain settings where you have small data sets, for example, because everybody talks about big data these days, but small data is also a very important problem to many firms, especially when they work in specialized products like special purpose lending, project finance, etc. But many settings, thank God, we have lots of data, so we can do learning. We can learn analytical models. And we can learn them in a supervised, an unsupervised, or a social network way. Supervised means that we have a labeled data set, so think of like an Excel sheet where you have columns with all the variables, where you have rows with all the observations, and at the end column, the ending column, the final column is a fraud flag that indicates whether a transaction is fraudulent, yes or no, or a person, one of your customers, is a fraudster, yes or no. Unsupervised learning means that you do not have that column with that fraud indicator available. So that means that you have to look at suspicious transactions or suspicious customers whose behavior deviates from the remainder of the transactions for customers in the data sets. In other words, you will be looking for anomalies. And an anomaly is not necessarily a fraudster, right? If you think of the salary of a person, for example, if you look at in Belgium, our national soccer team is called the Red Devils. If you're a bank and you're managing the salary of our Red Devils, obviously those will be anomalies compared to the rest of the population, but it's not necessarily fraudulent. But an anomaly typically warrants further inspection for fraudulent behavior. And then we have social network, learning, which I actually here put as a separate bullet, but which should not necessarily be seen as a separate bullet, because oftentimes social network learning boils down to building a network and featureizing it. That means like summarizing the network in a couple of variables, which can then be added to a supervised learning method like logistic regression, like random forest or XGBoost. Okay, so I guess many of those attending this talk have already some experience with fraud analytics models and have already made their feet wet in building analytical fraud models. But the question is, or one of the key questions is, how can you boost the performance of an analytical fraud model? And I think personally that you can do that in various ways, and that oftentimes when you look at industry, when you look at banks, insurance companies, or other firms facing fraud, the focus is wrong, right? I think the first focus should be, what would you want to do when you want to detect fraud? Actually, when you want to detect fraud, you want to cut your fraud losses. So if you're building an analytical model, you are not interested in maximizing a likelihood function or any kind of objective function like a mean squared error or a cross entropy error function, but you're interested in optimizing profit by reducing your fraud losses. So that's what we're going to focus on in this presentation first. Focus on the right objective, not on any type of statistical objective function, which is not interesting from a business perspective, but focus on profits or reducing costs. And then work on the data. It is my firm belief, having done quite a bit of benchmarking studies, that the best way to improve the performance of any analytical model, it's not by using random forest or XGBoost or deep learning or a convolutional neural network, but the best investment you can make as a data scientist is by doing data engineering, of which feature engineering is one particular topic that we're going to work on in this presentation. First of all, focus on the right objective. This is based upon a piece of research that it did with a PhD student, Sebastian Hübner, a colleague, Professor Tim Verdonk, and another colleague, Professor Wout Verbeke, where we introduced CS-logit, cost-sensitive logistic regression. It's in the second round of a well-known journal, and we hope to get it accepted soon. In case you would like to stay up to date, it's already available on arXiv. And what did we do in CS-logit? Well, if you look at traditional classification performance metrics, right, you will have performance metrics like the classification accuracy, like the sensitivity, which says like how many of the fraudsters do you detect, the specificity, how many of the non-fraudsters do you detect, and closely related precision, recall, and area under the ROC curve. However, what's really very important if you're building fraud analytical models, and if you want to apply those in a business setting, is that you focus on the right objective, and that you focus on reducing costs or optimizing profit, as I already said a few times. And there's different costs associated with different misclassification errors. And here you can see the confusion matrix, which you typically encounter in a fraud detection setting, and which we have complemented with costs. Costs of true negatives, costs of false negatives, and so on. So let's have a quick look at the headers of the row headers and the column headers, but it's basically just a classical confusion matrix. So the column headers say whether a transaction was actually legit or not. So then we have a negative, y equals 0, or whether we have a positive, a fraudulent transaction in case y equals 1. If we look at the row headers, the prediction can be negative. That means that we predict a transaction or a customer to be legit, in which case c equals 0, so my classifier output equals 0, or we can predict the transaction to be positive. That means we predict it to be fraudulent, in which case c equals 1. Then there's classification costs associated with it, and I think it pretty much speaks for itself that in case we predict somebody or a transaction as legit, and it is actually legit, then the cost is 0. If we predict it as legit and it is fraudulent, that means that the transaction is going to pass, and we're going to incur the fraud amount because the fraudster is going to be successful. So the classification costs of a false negative is that the amount of the transaction. If we predict somebody as positive, or a transaction is positive and it's actually legit, then it means that we're going to do the investigation, we're going to investigate the transaction, and then find out that it's legit. So we have the cost, an administrative cost, which is a fixed administrative cost relating to the resources needed, the human resources, any types of ICT-related resources needed for investigating the transaction, possibly also contacting the customer. The same transaction occurs in which, in case it actually turned out to be an actual positive, an actual fraudulent transaction or customer, because then we manage to actually halt the transaction and prevent the fraudster from doing all the damage. And then we're going to come up with a cost function. So the general purpose is to do a logistic regression. And why a logistic regression? Because a logistic regression is an interpretable model, right? You can very easily visualize logistic regression using techniques from credit scoring like scorecards or other nice visualization mechanisms like nomograms, for example. Nomograms are a very interesting visualization mechanism of logistic regression. If you'd be interested in any information on that, let me know. I will not talk about it now, but I will work towards building the cost function that is going to be optimized using logistic regression. So we have a set of big N transactions that's our data set, could be a set of customers, and we have a model trained on a set S. That could be any model, but we're going to assume that it's the logistic regression model further on, but actually the cost function can also be generally applicable to a random forest or an XGBoost, etc. And our classification model typically generates a label, classification label, which is typically based upon a probability or a score, right? The probability is between 0 and 1. A score is actually any type of number, like a log odds, for example, as it comes out of a logistic regression model. Then you can formulate your cost function as you see there. So this is the cost summed over all transactions by just going through your confusion matrix, appropriately covering each cell, taking into account the actual status, which can be legit or fraud, and the predicted status, which can be legit or fraud. So this is the cost function, which actually then we arrive at, which is also based upon earlier work of Baesens et al. In 2014. Reducing this cost function in its mathematical way gives the cost function at the bottom of our slide. And that's actually the cost function that we are interested in. To gauge the performance of our model, we need to have a baseline model. We need to have a reference model to see how much we improve upon a reference model. And the reference model that we picked, and you can pick another one, but the one that we picked is a model that predicts all transactions in the data set that's legit. In other words, it's going to pass all transactions, and it's going to let all transactions go as they are supposed to be done. So, which is class 0. The cost of this model, which is the cost of using no detection model, is actually the total amount of all stolen money, of all fraudulent transactions, of all fraudulent, of all money that was stolen by the fraudsters. So it just reduces then to the sum of across transactions of yi, which is the actual fraud indicator, 0 or 1, and the transaction amount of observation I, which is ai. The savings is then the cost savings that we managed to do with our model because of our model compared to that reference model, right? So it's the cost of the reference model, the baseline model, F0, minus the cost of our reference model, and we kind of express it in a relative way by dividing it by the cost of the baseline model. We work it out mathematically once more, which brings us to the formula at the bottom. These are the savings that we're going to use to evaluate our model. And then we have all kinds of information about transaction that you're going to put into your logistic regression, right? The more data, the better. And logistic regression has all kinds of very fancy ways of optimizing the number of variables that are really predictive, that are really important in your model, like stepwise logistic regression, forward, backward, and so on. We can also talk about various variable selection procedures, but we're not going to do that now. So we have the amount of the transaction, a timestamp, we have some info on the originator, info on the beneficiary. The more candidate predictors you have available there, the better is the lesson that we all know. and then just apply a variable selection mechanism, and that will give you a very interesting fraud model. And then we get our fraud score out of our logistic regression by applying the classical sigmoid transaction. The sigmoid transaction is just a transaction which bounds the outcome of our model between 0 and 1 such that it can be interpreted as a probability. And a classical logistic regression is then going to determine the unknown parameters like the beta 0 and the beta vector using maximum likelihood optimization. Actually, to be a little bit more specific, it's going to optimize across entropy error function. But as I said, that's not the error function that you want to optimize if you're working in fraud analytics, because you're focusing on you're not focusing on the right thing. You should be focusing on the expected savings or on the cost reduction. So what we're going to do is we're going to find those optimal parameters, beta 0, and the parameter vector beta. That's why it has been put in bold, because it's a vector. By minimizing the objective function with respect to our data set. Now, in the past, we've done that work also with, I saw that Sebastian Maldonado also joined us, some work with him on our EMP measure, expected maximum profit measure, that we applied for credit scoring and churn prediction. But the thing there was that it was impossible to calculate any derivative. But here, in this particular fraud setting, it becomes possible to calculate the derivative of our cost function such that we can apply a classical gradient descent method to find our optimal parameters. And to be a little bit more specific, our objective function is not only the average expected cost that we wish to minimize, but also the complexity. And there's various ways that you can measure the complexity, right? Model complexity can be measured by means of a rich regression, alike penalization can be measured by a lasso type of penalization term, or a combination of both, which gives you an elastic net. We opted for a lasso type of penalization, which is going to penalize the absolute values to the coefficients, as you see right here. So this became our cost function, where we focus on the average expected cost and then a lasso type of regularization. We calculated the derivatives. That was easily done, and then we applied gradient descent-based optimization. Here you can see on our data set, which was a payment transactions data set, which was provided to us. I can actually give you the name of the bank because it was in a research partnership with BNP Paribas, which is a pretty well-established and known bank. Here you can see if we applied it on our data set, and if we only focus, just to give you an illustration, on 2 parameters, here you can see the traditional logistic regression value that you would have for those 2 parameters together with the average cost here that you can see denoted on the color scale. So this is the traditional logistic regression if you would really optimize it using a maximum likelihood. However, if you would optimize it using our method, using our cost function, the question is, are we going to get close to that logistic regression point, yes or no, and what's the cost difference? So by doing the gradient descent, you see that you step in through this cost surface and that you actually end up in another point and a traditional point with a lower cost, which is not that surprising because we're actually optimizing what we're interested in, which is the cost. Here you can see the difference between both once more highlighted. So at the upper left, you can see the traditional logistic regression value optimum, whereas a bit lower here with the asterisk, you can see the parameters that we found using our model, just to show that both parameter sets are different, actually also resulting in different costs. Obviously, at the end of the day, you need to make a decision whether you're gonna have a transaction pass or stop, and that will depend upon the amount of transaction and the predicted probability of fraud. So to the left, you can just see some sample amounts and the predicted probability of fraud as they come out of your logistic regression model. And whether you're going to pass or stop the transaction obviously depends upon the expected loss. And the expected loss, in case you predict the transaction as fraud, the cost of actually doing the entire investigation, the cost of contacting the customer, inspecting the file, inspecting the transaction, and so on. Whereas if you predict the transaction as legit, right, it means you're going to have it passed. It still has a chance to be fraudulent, right? Because you're making the wrong decision. So the expected loss then becomes S times A. So you're going to predict it as fraud if obviously the expected loss of predicting it as fraud is lower than predicting it as legit. So when this inequality holds, which gives you this decision threshold based on work of Elcon, pretty obvious, right? So here you can see some examples in case we set the fixed administration cost to 10 euros. Whether you're going to stop, pass a transaction. Obviously, what will you anticipate if you would increase this cost? If you would increase this cost, that means it's going to cost more to investigate a transaction, and that means that you're going to pass more transactions, right? Because it costs you more to investigate it. So this is one way of improving the performance of your fraud analytical models. And we also showed that our CS-logit model, in terms of savings, expected savings, clearly outperforms a logistic regression model, which has been trained in the classical way. But there's more than just optimizing, than just changing the objective function. You can also do data engineering, right? And here the title of my slide says feature engineering, but I actually want to refer to the term data engineering, which is a term that we coined in one of our recent papers. And when we say data engineering, we mean if you look at a data set, you can engineer either the instances, the observations, or you can engineer the columns, which are your predictors. Engineering the instances is something that is really very important in fraud because you're typically faced with skewed data sets, which means only a minority of the samples or transactions is fraudulent. So you can carefully engineer those as well. You can do oversampling, undersampling. You can do smoothie, synthetic minority oversampling technique. You can do rows, RUP rows, etc. But you can also not work on the instances. Working on the instances is very important. But given that the limited time span I have to rush a bit. So we're going to work on the features. We're going to work on the columns, on the variables, and one of the features that we're going to work on are time features, right? Time is a very important aspect in any analytical model, but time is a weird aspect in the sense that if you look at the timing when transactions took place, it's not like you can consider time as a continuous variable, right? So there's no natural ordering in a time at which a transaction took place. Like if you look at 11 p.m., do you consider that to be lesser than or bigger than 1 a.m. in the morning, for example? So when you work with time-based features in a fraud detection context, it makes no sense to use the arithmetic mean to compute the average time set and to compute the arithmetic mean as a feature and add that to your fraud analytical model. Assume that I have transactions at 1 a.m. in the morning, 2 a.m., at 9 p.m. and 10 p.m., then the arithmetic mean is 11:30 a.m. in the morning, but no transfer was made close to that time. So it makes no sense to use the arithmetic mean to average a timestamp and calculate a feature as such. You can see this here. You can see this visualized. So you can see the blue bars indicate when the transactions were made, and if you calculate the average of that, then you get here, this is what you get. You get red dashed line, but no transaction was made anywhere nearby that red dashed line. So it's not, that arithmetic mean makes no sense. So we have to use another type of way of calculating intelligent, smart, time-based features such that we can see whether a transaction occurs at a suspicious time point, yes or no. So one way to do that is by using a von Mises distribution. And I didn't write down the formula of a von Mises distribution because it's a complex formula, and I'm underestimating your intellectual capabilities, but it's a series of Bessel functions, basically. Pretty similar to a normal distribution, but you can conceptualize it as a normal distribution wrapped around a circle, right? Which also has two parameters, an average, a mu, and a kappa parameter, which relates to the variance. And using the von Mises distribution and mapping it on your data then allows you to build confidence intervals. Here you can see confidence interval that we built, like a 95% confidence interval, and it also allows me to calculate the mean time when a transaction took place in a more meaningful way. Here you can see the red dashed line is the mean of the von Mises distribution, such that you now have your mean right occurring in the middle of your sample, in the middle of your timings, which makes a lot more sense than calculating the arithmetic mean, right? So now if we would have a transaction that falls outside, suppose like we have a transaction at 2 p.m. in the afternoon for this particular customer, we could see like, hey, this is really suspicious, right? So this could be a first indicator of suspiciousness. This could be a first flag and say, hey, this transaction warrants further investigation to see whether it concerns an actual fraudulent transaction, yes or no. Time-based features, I think, in any analytical model, very, very, very important. Besides time-based features, we also have social network-based features, because the general idea of using social networks in fraud is to build a network, and you're very creative in building that network. That could be a network of transactions, a network of people, or a network of multiple parties, like transactions and people, right? You can have unipartite networks in which you only have one node. Nodes could be like companies being linked to each other, or you can have a multipartite network, like a bipartite network, where you have like policyholders and claims, which are being connected to one another. We started studying social network featureization in 2017 together with my ex-PhD student Veronique van Vlasselaar, who now works at SAS. And we wrote a management science paper. Dolores already referred to some of my papers. That's one of them, the Gotcha paper, where we focused on predominantly on univariate featureization of social networks. Together, another ex-PhD student of mine, Maria Oskars, who's now a professor at Iceland, at the Reykjavik University in Iceland. We worked on bipartite social networks in an insurance fraud analytics context. And we recently got a paper accepted, Social Network Analytics for Supervised Fraud Detection in Insurance, in risk analysis. So as I said, the idea of social network featureization is that you have transactions like here, you have local features, and sometimes we call those intrinsic features, as well as we did in the paper with Maria, and then we add network features to them. Network features is actually a way of featureization. It's a way of featureizing a social network and enriching your data set such that you give your analytical model more opportunities to find something interesting, right? You give it more ingredients to actually find interesting patterns, suspicious patterns. But at the end of the day, what you still do when you apply social network analytics and fraud is that you still apply a supervised model, supervised analytical model, to find if the transaction was fraudulent, yes or no. And the most commonly used supervised analytical models that you're going to find are logistic regression. If you're into explainable AI, if you're into getting insight to why fraud was committed, logistic regression is a good alternative. Or XGBoost if you're more into, or random forest if you're more into performance of your analytical models, and if interpretation is less of an issue. Although, as we all know, there exists techniques like climb and values and counterfactual examples and ice plots to open up those black box techniques like random forests and XGBoost as well. So that's the general idea. That's work I did with that I'm going to elaborate on with my ex-PhD student Maria Oskarsdottir. And I already had some people asking me why this flag here behind me. This is the flag from Iceland. This is a present that I got from her when she graduated. And as I said, actually, some of the students that graduate with me actually give me presents, which is nice, right? Gotcha, here you can see Gotcha. I'm not going to talk about that. I'm going to of time. I see that this is still my old slide deck, but that's no worries. I'll find my way through it. Let's have a look. The BiRank, right? The work with Maria was actually an application, a kind of creative and innovative application of BiRank for detecting fraudulent insurance claims. And BiRank is a personalized PageRank algorithm for bipartite networks that was developed by he et al. In 2017. So it's actually quite recent. So if there are some PhD researchers amongst us joining today, I can actually highly recommend you to study that paper, because it's a really interesting paper with a lot of research potential across a variety of fields, not only in fraud, but also in risk in marketing if you want. It's a bipartite network. That means that it's a network that has two types of nodes, right? In our insurance setting, we will have claims and policy holders. These are two types of nodes, right? If there would be only claims, then it would be a unipartite network. But here we're gonna exploit the connection between claims and policy holders to see how the effect of fraud spreads through the network. By enriching the network, we're gonna be able to actually create more intelligent features, giving our analytical model more opportunities to find something interesting. The idea is to bring out nodes in the network that are most central from the perspective of a specific source node, the fraudsters. And the idea is to see how fraudsters are going to propagate their fraud influence by means of the policyholders and the claims to other nodes in the networks, to other policyholders and claims. And that will allow us to come up with very smart, intelligent features. You can see this visualized. You can see that I just came up with a very example network. The C stands for claim and the P stands for policyholder, right? And we can then see which claim was fraudulent, start from a data set like that, and then see how it's going to spread through the network using all kinds of propagation algorithms, using the propagation algorithm that was developed by BiRank, which is based on PageRank, right? Here you can see some of the technicalities. We didn't apply all of them in the paper. Time weighting is something that we did not do, but that you can consider, because we did not do it because we didn't find any added performance benefit when doing that. But you see that you have edges which are connecting the policyholders with the claims, right? So in this bipartite network, you only have connections between policyholders and claims, and you can have weights that are kind of decreasing in time, right? Whereby by taking into account the time since the claim, and by specifying a decay constant like gamma. The decay constant is a constant that you can set depending upon how you want, when you want the effect to be totally faded out. We have a fraud restart factor, which is actually our initial fraud labels, which can also be taken into account decay constant as specified on my slide. And then you have an iterative procedure that kind of starts, which is actually the application of a personalized PageRank algorithm in BiRank, where you have an exposure score of a claim and exposure score of a party, of a policyholder, which are actually iteratively calculated, as you can see right there. So in the first line, you can see that this is very similar to the Google PageRank, to how Google calculates its PageRank values, where you also have like this dampening factor alpha to dampen the spread of the fraudulent influence after a few iterations. And here in our technique, it was also set to 0.85, just as it's been set by Google. We then also have the exposure of the party, the fraudulent exposure of the party, which is related to the claim, and which is also calculated using a symmetric normalized weight matrix S, which has been calculated using the weights right here, and which has been calculated using two diagonal matrices, which correspond to the degrees of the policyholder and claim nodes in the network. This is actually needed to also ensure proper convergence of the algorithm. And here you can then see, like in the upper left corner, you can see that we started from a fraudulent node, a fraudulent claim, which is C4, and then we can apply the BiRank algorithm in an iterative procedure. It's going to spread its fraud influence through the network, and at some point you will see that some of these nodes will obtain high scores because they're getting a lot of fraud influence from different sides. Obviously, you have to imagine that this is a network where tons of nodes, multiple fraudsters that kind of influence claims and policyholders in various ways. So a claim can have a fraud influence or influx from various sides by means of the policyholders and other fraudulent claims. And then the idea is to featureize this, right? So you can look at, for a claim, you can look at various ways. You can look at the score itself, you can look at the minimum score, you can look at the maximum score, the median score, by the neighborhood of the claims, etc. And the way is the idea then is to featureize and then add these features to the data set such that your analytical model, which was an logistic regression and random forest, such that you will have more opportunities to detect fraud. So that's the whole idea. And there are various, BiRank is just one of them, other ways of doing that as well. But we found that to be very successful in our application. Here you can see that this is a screenshot from our papers for some of the results. We use the AUROC, but you can also use other ways of measuring the performance as well. The area receiver operating characteristic curve is still a frequently adopted performance measure because it has a very nice probabilistic interpretation, right? It's a probability that a fraudster gets a higher score than a non-fraudster. And here you can actually see that here you can see the information. We actually had two stats where we can contrasted the fraudsters from all the non-fraudsters and the known labels, which includes the fraudsters and the non-fraudsters, from all the unknown labels. Because in our data set, we also had a few claims of which we didn't know the label yet because they weren't investigated by the fraud investigators. And then you can see that the green curve gives us the performance in terms of the number of features. If we only look at intrinsic features, and then what color is this? I'm a little bit colorblind, but this is blue, gives us the neighborhood features. When we look at the neighborhood, whether there are any fraudsters in the neighborhood of a claim, the ratio of fraudsters in the neighborhood of the claim, is based upon a very important featureization technique that has been popularized by two very well-known researchers called Lou and Lisa Gator already some time ago. And then we have the score which comes out of the bipartite network. And obviously the best performance we get is if we combine all features in this way. Social network features that we got through the BiRank, through applying the BiRank on our data set, is really something that is that was really very useful and very performing. I still have some time, I think. I still have 5 minutes, so I'm going to talk a little bit more. So here we talked about defining fraud. We talked about fraud analytics approaches. We introduced cost-sensitive logistic regression. And we spoke about feature engineering. As I said, it's the best way to improve the performance of any analytical model, if you ask me, is by not that much looking at those new techniques, deep learning, etc. I think deep learning is a technique. I often get this question. And we recently did a benchmarking study which was submitted to eJOUR on deep learning, where we applied convolutional neural networks and Boltzmann machines and so on to credit scoring. And we actually found only very marginal predictive added performance when using deep learning. And that's the reason is because it's my firm belief that if you have structured data, like tabular data, like rows and columns, which you often encounter in settings like credit scoring, in settings like churn prediction, and settings like fraud detection, I don't think those complex techniques have a lot to offer. I think those techniques like deep learning, convolutional networks, etc., and autoencoders work really well if you're working with highly unstructured data like multimedia data, images, audio files, video files, etc. I think looking at those techniques will not give you a lot of added performance benefit in settings like fraud analytics. What gives you added performance benefit is data engineering. And in this setting, in this presentation, I focused on one particular type of data engineering. I focused on feature engineering and how to create intelligent features by carefully combining the columns or predictors of your data set in a smart or intelligent way. But you can also look at something else that we've been looking at recently and for which I do not have time to elaborate on, and that's at the instance level, right? Classical undersampling or oversampling techniques are often used for that purpose, but nowadays, recently, since the work of Chawla et al. On SMOOTHie, synthetic minority oversampling technique, there have been other techniques as well. One of which that we've been working on is ROP-ROSE, robust extension of ROSE, which is now also under submission with a journal to actually also do instance engineering in a smart way. So I think this is also very important to boost the performance of your analytical models. This was, in a nutshell, what I had to say. So I would like to, before I tackle the questions, I would like to especially thank Dolores and Emiliano for hosting this. I think Dolores has done a tremendous amount of work in setting up the NeEDS network, and I think for us it has been already very useful, the research group here at KU Leuven, for exchanging researchers and for learning new things and for writing papers together. And I'm not only speaking on my own behalf, but also on my colleague, Professor Jochen de Weert, who's also involved in this NeEDS proposal. And this has been very useful for us thus far. So thanks a lot for your efforts in that. Now, there's quite a lot of people, and we do have some time for questions. So if you have questions, I'll let Dolores share again. You can ask them in the chat box. You can also, I think you can also ask them by audio. If there are lots of questions, what I will do is I will pick the easy ones. No, what I will do is if there are lots of unanswered questions, you can send me by email, and then I will answer them. I'll try and answer them by email. Two more things. If you'd like to have more information about that, this presentation, you can have it. And secondly, you can also have a look at one of our Blue courses if you want more information. Ready to answer any questions you have, and I think I will give the floor back to Dolores now.
Thank you very much, Bart. It has been very insightful to see some of your contributions to fraud analytics. And so I think what I do is we open the floor, and as Bart said, either you raise your hand, or you write in the chat the question. And I can see that we already have a hand from Sebastián Maldonado. So could you, please state your question, Sebastián?
Sure. Thank you, Dolores. Thank you, Bart. Can you hear me?
I can hear you. I can see you as well. Good to see you, mate.
Yeah, good to see you, Bart, again. I hope next time I go to Belgium, thank you for recalling the presents. Next time I will bring your favorite Chilean wine.
Yeah.
Not only the students bring presents.
That's the reason I mentioned your name, actually, but anyway.
Thank you. My question is regarding the cost-sensitive logistic regression. I recall maybe an early version of the method, which called Prof-logit, which was tailored for churn prediction. In that approach, I think you did with Eugene. You used genetic algorithms for the optimization process, which was a little bit, sometimes depending on the setting, a little bit slow. I think the change that you did for this version, which is gradient-based optimization, is a very nice improvement. Can you tell me if you recall some difference in terms of performance in relation to using genetic algorithms for optimizing this cost-sensitive logistic regression versus the gradient-based method you suggested in these slides? Thank you.
Yeah, very good question, Sebastian. Thanks for asking this. We actually have three cost-sensitive analytical techniques. We have Prof-logit and Prof-tree, which is Prof decision tree, both of which have been developed for churn and credit modeling using GAs, genetic algorithms. The reason was because that we had to resort to GAs or genetic algorithms there was because of the complexity of the cost function. If you look at the EMP function, which we defined in the paper with Thomas Verbraken and Wouter Verbeke, that function was just too complex to derive. So we opted GAs there because it gave us a quick solution to find an optimum. And sometimes in analytics, if you have an optimum which is close to the global optimum, then that's fine. And we found that worked very well for both churn prediction and credit scoring. Now here in fraud analytics, the cost function that we defined, somebody is not on mute. Here the cost function that we defined for fraud analytics, the nice advantage that this had is that this was easily differentiable. So we made it quite easy on ourselves by defining the cost function, which was appropriate in the setting of payment transaction fraud, and which allowed us to differentiate it in a straightforward way such that we can apply gradient descent methods. But the cost function, the EMP function that we had in churn and credit risk modeling did not allow us to do that, so we had to resort to GA's, genetic algorithms instead.
Okay, I think thank you, Sebastian. I think we go to the second question from Wolfgang.
Yeah, may I speak? Yeah. Thanks,
Please.
Bart, for
Sure.
a great presentation, super. I think your PhD student from Iceland, she should have worked on the Wirecard data. Then we would not have had this country. Wirecard. This is the company
cool.
that's the company that is bankrupt now because of fraud, right?
Oh, yeah.
And that brings me that brings me to the practical question, namely, I like the social network approach there, but do the banks really on, say, EU level have a chance to actually follow these network links down to Philippines, down to Russia, down to wherever, because that's where the money is sunk finally. Yeah, I mean, this is a practical question, but you have so many industry contacts, and I understand NeEDS is a network that also involves industry as well. I would like to. I understand this completely mathematically, and for a small little bank around the corner, that's absolutely clear, right? But that would be one question.
Obviously, your data set is always limited to its perimeter, so you cannot go out of scope of your data set, right? So in this particular case, the work that we did with my colleague was with AG insurance, and the restrictions we had were based upon the information we had. But I know that there's European initiatives for exchanging data amongst banks, and that's interesting not only in insurance, but also in credit risk in various settings. But that data is not being leveraged yet for any analytical purpose, to the best of my knowledge.
I see. And maybe I add one more thing. Of course, the sigmoid function, the logistic CDF, right, is of course too close to zero. That's why you have to use genetic algorithm to jump out. But is there some kind of an LSTM analog, or that you could kick in that helps you to get out of your vanishing gradient problem? You mentioned genetic algorithms. Yeah.
You could, well, here we didn't use genetic algorithms in this presentation because we managed to compute the gradient. So here we managed to do that. Here we didn't have the problem. The sigmoid transform was perfectly fitting our needs. Obviously, you can look at hyperbolic tangent transforms, but it's not going to add anything at all, believe me. But in the other setting, LSTM, I don't. My empirical intuition says it will not add anything, but it will not solve our problem because our cost function is too complex.
Okay, thank you.
Luis, I see that you raised your hand. Good to hear you.
Hey, Bart. Thank you for the presentation.
You as well.
Yes.
¿Cómo estás?
Good to see you. Very good here. So, Bart, I got a couple of questions. First is about this cost-sensitive logistic regression. Is there any interpretation about the difference in this beta estimated compared with the optimal logistic regression? For example, if these new betas are detecting more or some specific variable are more related to extreme values fraud, so some kind of interpretation about the new betas you get compared with the previous well-known solution. And the second question is about some feature engineering or relate some kind of bias you can have in the data, especially on fraud detection. Maybe you can have some bias in the detection, or when you have some policies that trying to detect some fraud, maybe they are correlated to some features. For example, I don't know, some kind of ethnic bias. And I don't know if you're familiar with some tools to clean or trying to help the model to to clean this kind of bias?
Yeah, that's two difficult questions, but first of all, about the beta parameters. The beta parameters of logistic regression in our CS-logit are tuned now differently than in a classical logistic regression. Now they're tuned to detect fraud in a cost-sensitive way. So they're tuned completely different. So they will be different and they will have a different interpretation. But the question we struggled with when we wrote the paper does not that much relate to the beta coefficients, but it related to the outcome of the model, the score that comes out of the model. Think of it as the log odds. Because what makes logistic regression gives you probabilities. It gives you probabilities because of two reasons. It gives you probabilities because of the sigmoid transformation, and secondly, because of the maximum likelihood optimization, because you're maximizing the probabilities in the likelihood function. Now, the scores that come out of our method, we still use the sigmoid function, so they're still bounded between 0 and 1, so we can interpret them as probabilities as such, but that interpretation is not that straightforward because we abandoned the maximum likelihood optimization. So it's more of a ranking in terms of maybe fraud severeness that comes out of the of our CS-logit than a pure probability that in a classical probabilistic way. So the beta coefficients, I mean, they're tuned to find that fraud, but what was more difficult for us to interpret the scores that come out of the CS-logit, which turn out also to give us quite good ranking behavior when compared to the classical logistic regression, which further corroborates our empirical intuition that they are correlated to probabilities. To answer your second question, the feature engineering and the ethnic bias, obviously that relates to the data elements that you put in. And ethnicity, and it relates to ethics and AI, it's a very difficult topic. Because we all know that the most interesting pieces of information in any analytical exercise are gender and age, but obviously in many countries you cannot discriminate based on gender and age for insurance, for credit, or for whatever type of marketing action. And that relates more to the ethics and AI perspective, which we didn't tackle in our course, but which is also very important in feature engineering, because the complexity that you may have there is that you start engineering gender-related features which do not look like gender features at first. Let me give you one very stupid example. Say I would, it's gonna sound stupid, but it's gonna illustrate my point. Say that I would engineer a feature which is your shoe size. We all know that the bigger your feet, the bigger your shoes, the more likely you are to be a bad payer, the more likely you are to be a fraudster. That is true. That is, you will find a positive correlation. Why is that? That is because women have smaller feet, but you have engineered a feature, shoe size, which kind of measures the gender effect. That's the point I want to make, right? And it's not because you cannot use gender that you can use shoe size, because with shoe size you're measuring a gender effect. So you see how complicated it can get. You can start without knowing it, because now this is a stupid example, but without knowing it, you can start engineering racial bias features, you can start engineering gender features, and that's something you should be aware of, right? And that's something that is that you should be carefully be monitored, that you're not latently introducing any ethnic or gender bias into your models by engineering those features. That's true. I hope that answers your question up to a certain point.
Sure, thank you.
Excellent. Any other questions?
It seems Dolores is having some internet problems, because it seems.
What about now?
Okay, now perfect.
Yeah, apologies. So I was saying that we thank you very much because you have brought us the need to change our objective function in some of our machine learning models, depending on the application. And in this case, yeah, we have seen that this makes us change also our optimization procedures for this machine learning. So it has been very insightful, and you have touched on very important topics such as Luis was talking about, discrimination, but also other important issues in machine learning. So it has been very, very good to have you, and very enjoyable.
Thank you very much. It was good to see some known faces back again, and thanks everybody. And let me know if you would have any follow-up questions.
Thank you. And for the audience, please remember that on Monday we will be back at 4:30 with another presentation. This time it will be on power systems and the interplay of machine learning and optimization. Thank you all.
Thank you.
Thanks. Bye-bye. Take care.